Okay, in this video, I'd like to talk a little bit about domain and range of functions. So in my previous video, I defined what a function is. Now I'd like to look at the definition of domain and range. So the domain of a function is the set of x values. I think of it as where x lives. That helps me remember it. Where does x live? That's our domain. And the range is the output that is the set of y values. So domain, you asked a question about domain, they're saying what different x values can you potentially have? And range, the range of y values that we get out of a function. Okay, now once again, functions come in a variety of formats. So my first example here is just a set. First, let's check that it is a function. So for each x, is there only one corresponding y value? Well, we have 4 distinct x values, so yes, it's going to be a function. So in this case, where I just have a finite set of points as my function, my domain will just be a list of the x values. So make a curly bracket to represent set, and then I'm just going to list my x values. 6 and 2. And I'm not particularly, that's a terrible curly bracket. You get the idea. I'm not even particularly concerned about putting them in order. My math lab may want you to put them in order, or you may need to pick from their choices. But my domain is simply a list of the x values for this function. And for my range, going to be a list of the y values for this function. Now, the y values repeat, which remember is okay, it can still be a function, but since the 0 repeats, I only need to list the 0 once in the set. It doesn't make sense to list it more than once. So 0, 5, and 3, and again, you can put them in order if you want to, but this is perfectly fine. 0, 5, and 3, that's all my possible y values for this function. Now, most of the time, we aren't going to be looking at just sets of values. So the next 2 examples that I have are graphs. So in the first graph, and we don't run into this too much, but suppose I have a graph such as this one where it has endpoints. So the graph stops here. So it's restricted. It may have a limited domain and range. Now, unlike the last example, I have infinite points, though. Now, I have way more than just the 3 points they list in the picture. There's all kinds of points all along this graph that are x and y values that make this function true. So how am I going to list the domain? Well, I'm going to use interval notation. This is the same notation we use to express answers to number lines, and this involves using certain parentheses. So in the previous example, I had a set of individual values. I used a set notation. Now I'm going to use interval notation. And refer to your book and your teacher on what notation they want us to use, but here interval notation makes sense, although not the way that I spelled notation there. Notation, okay. Okay, so the domain, this is the x values, and think about where x is at on a graph. Here's our x-axis. The x value tells us how far left and how far right to go. The x value is the first in the value of an ordered pair. So for this graphic, the farthest left it goes is -3. And I have a solid point at -3. So to show that I include the -3, I use a square bracket to indicate -3 and that I am including that -3. Okay, the highest x value, the furthest right that it goes, apparently is 8. And again, I put a square bracket to indicate they've given me a solid circle there to let me know that that 8 is included as part of my answer. Let me clean up some of my mess here. So that's my domain, the x values. And we would list that low to high. Low to high. And for x, that's going to be left to right. Okay, so what about the range? Well, the range is going to be the range of y values see if I can do a different color here. So the low to high for y is going to be up, down, low to high. Now it just so happens that my low y value, I can see on both points there, is -3. And the highest it goes is apparently 10. Okay, so my x values only go from -3 to 8. That's my range. My y values only go from -3 to 10. That's my range. Okay, what if I have a graph that has some arrows on it, as our functions often do? What would happen then? Well, my domain, again, is going to be how far left and right my graph goes. Well, the arrows indicate that it keeps going. In fact, it keeps going on forever and ever and ever. And so I need to use infinities here. What's the furthest left this line goes? It goes all the way to -infinity. Now, in interval notation, we always use curved parentheses with infinity signs. That's just the rule in math because it's not an actual solid finite number, right? It's infinite. And how far right does it go? Well, eventually, right, it's going to keep going up, but as it's going up, we're also going over. So domain and -infinity to infinity. And what about the range? Actually, the same thing. So often we can think of domain in general as everything, all real numbers, -infinity to infinity, unless the graph has some endpoints on it or some restrictions on it. So that's how we can get domain from a set, domain from a picture. What about when we have equations? Now I'm going to say that when we have equations and we don't know what the graph looks like, then I'm only going to ask about domain in my class because my students don't know what the graph looks like. It would be hard to answer questions about the range. So we're going to stick to just figuring out the domain. So now we're thinking about, again, x values, but not only x values, that's annoying, sorry, x values, but what can x be? So this is going to be really important to think about domain, especially when we start solving equations. So for instance, y equals 3 over x. And we encountered something like this earlier. So what can I plug in for y? I can plug in, what can I plug in for x? I can plug in 1, -1, I can plug in 3, I can plug in 6. I can plug in all kinds of things for x, but there's one exception that I can't plug in for x because of where this x is located, and I hope you know what it is. Right, a big rule in math, we can't divide by 0. So I used to think domain was really hard, but it turns out there's really just two main rules. We can't divide by 0 is one of our major rules. We can't divide by 0. Now, in this case, 0 itself is an issue. It makes this undefined when I plug in 0, so I'm not allowed to plug in 0. So what am I allowed to plug in? Well, basically, we're allowed to plug in all real numbers except 0. Now, there's a couple ways we can write that. One is set notation. We would put set x, straight line, we read as such that, and then we would just make a list of things that x can't equal. You could do interval notation here. So instead of -infinity to infinity, we would say -infinity, I get up to 0, I don't include 0, so that's a curved parenthesis, and then I pick up again, union, 0 on to infinity. So there's 3 options on how you can write it. Ask your teacher how they want it. Now, a lot of students take this to mean x can't be 0 in these rational expressions, but that's not necessarily true. So if I look over here at 3b, now I have a more complicated rational expression with x's on top and bottom. But my issue is only with the denominator. And so our question becomes, what values of x make my denominator 0? So only the denominator. Why not the numerator? Well, because I can have 0 on the top. 0 divided by a number is fine. But dividing by a 0, never okay. So now I have to figure out x squared minus 4. When does that equal 0? So do you know how to solve x squared minus 4 equals 0? Do you remember? So since it has an x squared, this is more of a quadratic. First thing we can try is factoring. Okay, let's see. So x squared minus 4, that's one of our special patterns. That's a difference of squares. So this factors to x plus 2, x minus 2. I would also accept adding 4 to one side and then square rooting it, but you'd actually get two answers, a positive and a negative root. So there's two values of x, think about it, negative 2 and 2. When I square them, they both give me 4. So these values are actually not allowed. So again, we would write the set of x such that x is not negative 2 or 2. And your teacher may even accept it just to write it out in words, to say something like all real but negative 2 and 2. And that's all that I'm writing here is set notation. All right, that's rule number 1. Rule number 2 is we can't square root. It's terrible. We can't square root negative numbers. So y equals the square root of x. I can square root 1. I can even square root 0. I can square root 4. I can square root 2, even though it's irrational. But what can I not do? I can't plug in something that's negative here. Try it in your calculator. The square root of negative 1, your calculator is probably going to say error, because this is something that when square rooted gives us a not real value, which we aren't interested in. So what am I allowed to plug in? That's what my domain is. I can't plug in things that are negative. What's another way of saying non-negative? I am allowed to plug in 0 and anything bigger than 0. So the domain for just the square root of x, 0 to infinity, including the 0. Now where it gets a little more complicated is when there's more things under the radicand. So the next one now has not just an x, but an x plus 2. And I used to kill myself trying to do these in my head. Here's what we need to say. X plus 2 can't be negative. X plus 2 needs to be greater than or equal to 0. So what can I plug in? I can plug in things that are negative 2 and higher. Okay, now what about the range for all these? Don't worry about it, because we're only going to ask in my class when you have a graph, what kind of range are the y values going to come out to be? So since we haven't talked about the graphs of these yet, I'm just worried about the domain. But it's a really important concept because the limits on the domain are going to affect how we solve some of our equations. All right, so I hope that answers how to find the domain.